Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is the International Space Station Transit of the Sun. And here to tell us all about it are Tim Campbell and John McGill, both members of the Ford Amateur Astronomy Club and Solar System Ambassadors. John, welcome to the show, and Tim as well.
Yeah, hi, Don.
And thank you for having us.
Well, you're welcome. Now, we're going to kind of continue with the sun theme. Last month we talked about the solstice, and this month's program involves the sun as well. Now, I'm sure to capture a transit of the ISS across the face of the sun, you have to do some planning. What do you need to do, John?
Well, let's get started here. I want to share a screen here. This is a app that you can download for free. It's called the Iss Transit Finder. You can auto-detect your location, or you can select from a map where you're at. So if we go here and let me select from the map, now we have our coordinates, and then from the time, so we'll set it, take the default settings, and that takes us out till July 18th. And then we can go for kilometers, so 80 kilometers, I think that's probably, about 50 miles or so, something like that. So that says we're willing to travel 80 kilometers. And so if we hit the calculate button, that's going to tell us what transits are going to be available that we can see. Now this is on the 4th of July, and that's showing a pretty close one. When you're on the center, you're actually going to be, the center of the transit's going to be on the center of the sun, which also gives you the most time of the transit. So this transit, the duration is 2.78 seconds. And that's actually a long time for a solar transit. The transit that we imaged, that one was only 1.17 seconds, so less than half the time. And it still was down the middle. So it's really something that you have to work at. You have to be at that exact location at that exact time to capture that ISS going across the sun. And the reason why I'm enlarging this is we want to find a good area where we can image this at and set up our telescope so that we're not going to be hit by cars like off the side of a road. We want to actually find a park. So it looks like there's a few spots along here. Here's a golf course. So if we were at this far end of this golf course, let's just hit that for sake of hitting it. You can see we're only off a little bit off center line, but it's still at 2.78 seconds. So we really haven't lost anything on the time. And there it is, still right in the center. Yeah, Tim's going to talk now about some of his image that he took of a solar eclipse, which is actually an eclipse of the moon going in front of the sun.
Yeah, so this image is really best look at it sort of backward, read it right to left instead of left to right. As the moon begins to cover the sun, it first comes in from the left edge of the sun as we look at it here on Earth. So this image in the upper right shows the moon starting to block the sun, and that's taken with a solar filter. We'll talk about those shortly. As it continues to cover more and more of the sun, you get the image that we see in the middle. It completely covers the disk. If the moon is sort of close enough to the Earth, the moon appears slightly bigger if it's closer to the Earth, and just slightly fractionally smaller. You get an annular eclipse if it's a little farther away. But this one was a total eclipse, not an annular eclipse. And then as it starts to go away off the other side again, you see what you see in the lower left corner with the sun starting to be revealed.
And how long does that eclipse usually take?
That was just a few hours. When we did the timeline, I think it was a little less than 3 hours from the moment the moon first just starts to take a bite out of the edge of the sun until it completely leaves the other side. Now the part in the middle, where it's totality, that it depends again on how close are you to the center line. Could be a minute, could be a couple minutes, but it's usually not very long. Usually not more than maybe 5 or 6 minutes for even the longest eclipses. This is a transit of Mercury. Mercury is a little closer to the sun, and we get a handful of these per decade. And you can see Mercury is moving across, but it's just a tiny, tiny little dot. You wouldn't see this probably without a telescope. Certain eclipses, like transits of Venus, you could see with some eclipse viewers. You wouldn't even need a telescope, but this one you probably would. The dot's a little small. It's a little hard to see that one.
Yeah, and that actually took about 4 hours, so it's quite a long time for that one also. And here we have the Venus transit in 2004, and you can see how much larger Venus is in this. Uh, this is actually a time lapse. So in a time lapse, what we're doing is condensing down the time because it takes so long. So we want to make it something that's viewable in a short duration. So that's another about 4 to 5 hour transit that's down to less than a minute. The next transit of Venus, I don't think too many of us are going to be around because the next one doesn't happen until
Yeah, you get
2117.
4 transits only in I want to say it's a 2045 year cycle. And they're both, it's about 108 years between one transit, and then 8 years later there'll be another one, and then it'll be almost another like 105 years. I'm doing all this from memory. My time is off a little bit probably, but it's more than a 100-year span. So we had a 2004 transit and a 2012 transit, and that was the 8-year span, and now it's more than 100 years for the next one. This is a NASA image showing the actual International Space Station. So what we tried to capture was the space station transiting the sun. You're going to see it as a silhouette, of course, because the sun's very bright and the space station is not. But this is a photograph of the International Space Station, the actual space station flying above the Earth. You can see those solar panels all spread out there. That makes it occupy a fairly large area. And for comparison,
Yeah, here we got the actual space station superimposed over a football field. And so the full length and width would be about the size of a football field with the solar panels. And if you look at the solar panels, you see up at the top left, you got 4 solar panels there. In the bottom left, you got another 4, and the same on the right-hand side. Well, if you take 2 of those solar panels and you put them together, that's about the size of the large full-size school bus. So that kind of gives you an idea of what we're looking at. So you take this and you put it in front of the sun, which is about 100 Earth diameters wide. You'd think that you wouldn't see something that's only a football field wide in front of something that is so big, but in relative distance, because the space station is 250 miles generally above the Earth, it looks quite large. It's somewhere between, you remember those videos that we showed of Mercury and Venus, the dots? Well, it's a little bit bigger than Mercury, but smaller than Venus.
Well, it looks like the only constant in all of these transits is the size or diameter of the sun.
that varies just a tiny bit, right? The sun's roughly 93 million miles away, but during part of the year, it's a couple million miles closer, and the other 6 months later, it's a couple million miles farther with about a almost 4 million mile variance in rough round numbers. It doesn't make the sun dramatically seem much bigger or smaller, but if you measure it carefully, it's just a tiny bit.
We've talked about planning and what you can use to help you know where the transit is going to occur. Let's talk about equipment. What do you need there?
What I have here is an actual solar filter. This is a piece of film. Some of them are film, some of them are glass. But this is coated, and it looks like a mirror probably to the camera here, but it is actually transparent. But the problem is even if I hold this up to a very bright light, I wouldn't see anything. This filter is blocking out 99.999% of all the light. That means 1 photon out of every 100,000 makes it through. To be safe, you have to block out 99.996 or more. So this blocks out a little bit more than what is required to be safe. If you don't do that, you can damage equipment, and certainly that equipment could be your eyeballs. So you want to make sure you're very safe.
In this picture here is my telescope, and that's another club member, Jerry. I didn't want you guys to think that I shaved after this picture was taken. That's my filter on top of my telescope, and it's just a little bit larger because I have all-around telescope that I use that I get good images and good observations of deep sky dark objects, along with I can image the sun and view the sun with that filter on it. And I know Tim, he has a different type of setup where it's specifically for solar viewing.
Yeah, so here's a image of my setup. It's actually two telescopes. The telescope that you see on your left is the one that I did my imaging with. The one on the right is another one of these all-round telescopes I can use for anything. That's a refractor. I was able to visually watch the space station fly through that telescope while the camera captured the space station through the other telescope. The one on the left is kind of special, though. That one is it's called a hydrogen alpha solar telescope. So instead of just dimming the light, the sun, like a incredibly strong pair of sunglasses, what it's doing is it's actually blocking out all wavelengths of light except one, and that's the wavelength, the dominant wavelength that hydrogen atoms emit, called the hydrogen alpha wavelength. That telescope is able to observe the sun's chromosphere, so it sees all the really cool, interesting swirly patterns on the sun.
This is back to my telescope that I used. And what you see on the top of it, and that's wrapped in tape, but that's a solar finder. You can see that little white dot in the center. That's how I know when my telescope is pointing directly at the sun. And this is a homemade solar finder that I made. And what the circular part is actually a empty caulking tube that I, knocked both ends off, and I actually put a piece of tin foil on the front and just poked a hole with a pin in it. And so that pinhole, when I'm lined up directly in the center of that salami slice on the back, is when I'm focused or framed directly on the sun. So that's how I get my framing.
Well, if you don't have any equipment, one of the things that you can do with the telescope is you can't look at the sun with your eye. You can look at the ground and adjust the telescope so that the shadow of your telescope is a circular spot on the ground, and instead of the tube. That'll get you close.
So Tim, what type of camera are you using?
This is the camera here in my hand. It probably doesn't look much like a camera that most of you are familiar looking at. This is a camera that's specifically designed for astrophotography imaging, and this one, and there are lots of these. I actually own a few of them with different specialty purposes, but this one is designed specifically for solar photography. And you'll notice there's no shutter button, there's no viewfinder. You plug a USB cable in here, it has to be driven by the computer. What makes it special for solar imaging is it has an incredibly fast frame rate, something like 168 frames a second that it's able to capture, which is actually kind of important when you're doing the sun. And it turns out it works great for this event, which is capturing the ISS.
Well, John, what about you? What camera do you use?
Yeah, I use a Canon camera. This is a DSLR, and this is actually a sports camera, and this is one of the highest frame rate cameras that is a DSLR without going into the new, what do they call those, Tim?
Mirrorless.
The new mirrorless cameras. This one has a mirror in it. So this one can take 14 frames a second, and that's actually what I captured my image at. And when we get to that, you'll see each actual 14 frames.
Well, how do you go about making sure you got the timing right for photographing the ISS transit?
Well, that's another thing. There's another app that you can put on your phone or however you want to get the time, but you need time down to the correct second. So we'd like to use U.S. time clock, and you can bring that up on your cell phone, or if you're like Tim, you can have Apple Watch, which that will be an atomic clock timing, as
Pretty much
precise as
any
you can
cell
get.
phone gets its time off of the cell phone company. They synchronize, those carriers synchronize their time to the U.S. Bureau of Standards, and so that the clock on your cell phone typically is accurate to the second. And it just happens that my watch is synced to the time on my phone, so I benefit from that as well, and I can just look at my watch.
Anything else that you need to consider before you actually start taking images?
Yeah, one other thing that you might want to consider is a triggering device. It can be wired or you can have a wireless, but basically what it is, it's you don't want to shake your telescope or your camera when you're pushing the button because that will blur your image.
Yeah, mine is simply computer software, so all I have is a USB cable connected to my camera, and that means I tell the software when to start capturing. The important point is that I don't have to touch the equipment so I don't get the shake.
Good point indeed. Well, I guess we're at the point where you guys are going to start taking images, but we're also at the point where we need to take a break. Now, if you have any questions, you can send us an email. The address, as always, is down at the bottom of your screen. And coming up next with Term of the Month is Stephen.
Thanks, Don. The term of the month is solar rotation. The sun rotates on its axis about once every 27 days. This rotation was first detected by observing the motion of sunspots. That had to wait for the telescope, even though sunspots were known before telescopes. The sun's rotation axis is tilted by about 7.5 degrees from the axis of the Earth's orbit, so we see more of the sun's north pole in September each year and more of its south pole in March. Since the sun is a ball of plasma, it does not have to rotate rigidly like solid planets and moons do. In fact, the sun's equatorial regions rotate faster, taking only about 24 days, than the polar regions, which rotate once in more than 30 days. The source of this differential rotation is an area of current research in solar astronomy. And that is the term of the month, solar rotation. Back to you, Don.
Thanks, Stephen, and welcome back. We're here talking with Tim Campbell and John McGill about the International Space Station Transit. Okay, guys, we've planned, we've got our location, we've got the equipment set up. How about we take some pictures?
Yeah, that's a good idea, Don. What we did, we were all set up, and so now we're starting our countdown. And so now at about the T 20 minute, I call it T like a launch, but at about 20 minutes before the transit's supposed to take place, we're starting to go through and do our test shots, trying to make sure we got focus and thinking about did we miss anything. Everything's going through our heads right now. How about you, Tim?
Yeah, and so on earlier attempts, I've missed this thing. So, I thought I had everything ready, and I did the recording, and I'm, visually looking through one scope and recording on the other scope, and the timing shifted. So you got to double check the timing.
Yeah, and then we get down to 5 minutes, and now the anxiety is really starting to build. So we take a few last-minute images again. I mean, just want to keep making sure our camera's still working, still functioning, and we also have to make sure that we still have the sun framed in our camera, because the sun is moving, and we're using tracking telescopes, but still, we want to just, right there, right in the center, we want it to be perfect. So then we keep counting down, and I think about 45 seconds to 30 seconds before the transit, Tim started doing something.
Yeah, so on my first attempt to do one of these things. The transit finder will tell you exactly to the second when the transit will happen and down to the hundredth of a second how long things are going to last. And so I thought, I got this. I'll just start recording a couple seconds before and a couple seconds after, and I'll get it. And of course, the time shifted. So now I'm really going to hedge my bets. I tell the camera to start recording 45 seconds before it's supposed to happen, and I keep recording 45 seconds after it's supposed to happen. So I make sure I'm going to get this thing. And I'm calling these times out to John across the field.
Yeah, so we get down to T-minus 30 seconds, and I press my shutter button at 30 seconds to go. And what you got to remember is on a DSLR, it'll only take so many frames before the buffer fills up. But as Tim mentioned, he didn't get the first one that he attempted, and I didn't get the first one that I attempted because, you get so anxious and you want to start early. So I started again early, and then my buffer filled up. So it was still about 15 seconds before the time was supposed to start, or the transit was supposed to start. So I had to let off my trigger and hope and pray that my buffer clears out before we get to the actual transit time.
Yeah, so as we got down to 10 seconds, and John's like, call it out, Tim. And so I'm calling it out, 10 seconds, 9, 8, 7, 6, 5, 4. By the time I get to 2 seconds, and then John...
Yeah, then I start taking my pictures, and all I can do is hold the trigger down, and I hear my camera going off like a machine gun. It's shooting frames, and then about a second after it was supposed to go by, I hear Tim yell out.
Yeah, I was like, yeah, it's over. I just saw it. So my computer setup allows me to see in real time what the camera sees, and so while we're counting down these times, I literally watch the satellite fly across my monitor, and I yell out to John, "That's it, it's done."
Well, I guess you guys did get your video and your images, so what now?
Yeah, now we have to process the images. So I do a little bit of color adjusting in Lightroom where, you can do a little bit of sharpening, and you put in some, actually, I want to call it like a fake color on the sun to make it look more natural to what we look at. Because when you're shooting through a white light filter, it actually makes the sun look white. So a little bit of cleaning up in Lightroom, and you can add a little bit of clarity to the image, and then anyways, it comes out pretty good. And Tim, what did you do?
Yeah, so on my side, I capture these frames in a format called .ser. It's kind of like a movie file. Each frame is a full resolution. There's no compression, and so it's like a raw footage. And then I have software that will convert that into a series of individual frames, which I then pull into Apple Final Cut. And then in Apple Final Cut, I'm able to turn that into a movie. I do the same thing John does. I have to adjust the color. My camera is actually a monochrome camera because in a hydrogen alpha telescope, only one wavelength of color comes through. So you don't need a color camera. So I do adjust it to colorize the image.
This was the first transit that I caught in 2019. And that little dot in the middle, that's actually the ISS. And you can see that the sun is basically blank in this image. There was no sunspots to focus on. And if we can go to the next image.
Yeah, so this is mine, and if you watch, you'll see the ISS. So this is what I see. Now, as you're watching this, it's taking a while for the ISS to come across the sun. In fact, this entire thing happened in just barely over a second. So we're playing this back in slow motion to kind of stretch it out. You can see the detail of the sun's surface. That's what you get out of a hydrogen alpha telescope.
This is one of an individual frame. Now, this one I cropped in so we get a little bit clearer picture or a bigger image of the International Space Station. In this one, you can see the solar panels on each side. It kind of looks like a starfighter.
Keep in mind, this space station is flying at about 25,000 feet per second. So even if you have a shutter speed of, say, 1,000th of a second, that's still 25 feet that this aircraft or the spacecraft flies while your shutter is open. So don't expect absolutely tack sharp.
And we were shooting through a very thin but high layer of clouds, so we weren't in perfect conditions. And that's a sunspot there to the left.
Sorry.
So you can see the high speed shutter action in here. So this was 1.17 seconds, and I caught 17 frames in this image. And this one was blended in software called Star Stacks. And so this is a composite of 17 individual frames.
Well, I guess the biggest piece of advice that I've gotten from this conversation is three things. If you want to take pictures of the transit: practice, practice, practice. I want to thank my guests, Tim Campbell and John McGill, for bringing us this fascinating topic. Please check our website, the Ford Amateur Astronomy Club website. The address is down at the bottom of your screen. And coming up next with What's Up in the Night Sky is Stephen.
Thanks, Don. What's up in the night sky for July 2021? July starts with the moon in the last quarter on the 1st. The new moon is on the 9th, the first quarter is on the 17th, and the full moon is on the 23rd. Now, lunar perigee is on the 21st, so this is pretty big as the moon goes. Mars and Venus are shown here on the 1st of July. They both go from Cancer to Leo and are shown just a little bit after sunset. On the 1st, Mars and Venus are 6 degrees, but on the 31st of July, Mars is 1.5 degrees from Regulus, and they are about the same brightness. Mars is the red one. Binoculars should show the pair easily. Uranus is in Aries, Neptune is in Aquarius, Jupiter is also in Aquarius, Saturn is in Capricornus, and then on the next image, Pluto is in Sagittarius. Now, Pluto is shown very close to the horizon, and Saturn and Jupiter are not that far from it. Now, Pluto has opposition on the 17th. There are two comets, one in the northern hemisphere and one in the southern hemisphere, that should be visible this month. 7P Pons Winnicky is brightness 10.1 and is in the southern constellation Sculptor. C 2020 T2 Palomar is a little dimmer at 10.6 magnitude and is in the northern constellation of Boötes. And that is What's Up in the Night Sky for July 2021. Remember, we don't charge for this show, but we may tax your brain.